Hi everyone. I'm having some problems with my editing software, so hopefully we can get through this in one take. Good luck. So we're sort of wrapping up the 1 Newton challenge, and I want to look at the different solutions we've talked about so far. And the question we had was, what is the price that we have to pay for using less force? So we're just going to look at one of the possible solutions and see if we can figure it out. If we take our ramp and we pull up the mass, this thing worked just fine. But I want you to think about it. If you've ever walked up ramps, you know that it kind of takes a while to work. I mean, it's generally slower to walk up the ramp as opposed to just, going straight up. Um, if we go ahead and we just took the mass and we raised it 10 centimeters, or this is 0.01 meters, well, this thing just would take 1 Newton of force. Here, though, we don't only move at 10 centimeters, we move at a much longer distance. Say, for example, we moved at like 40 centimeters or 0.04 meters. This is a much longer distance, but we get to use less force. So the price we pay is if we want to use less force, we're going to need to go a longer distance. And that's true for all of them. That's true for the lever with the fulcrum. That's true for the two different wheels. Um, it's true in each of these cases. In fact, if you do this perfectly, the best that you can do is this. The force that you apply, I'll call it force A, times the distance that you apply it will always be larger than or equal to uh, that force of gravity times that 10 centimeters, that distance that the mass is traveling. This right here is special. This is that price that we pay. You can kind of think of it, this is the cheapest that we can get this thing off the ground. Our total force, um, sorry, like I said, editor's busted. Let me say this a slightly different way. Um, we know that 1 Newton times 0.01 meters. That's the force we're using times the distance traveled. No matter what we do, the force that we use times the distance traveled is going to have to be at least equal to that. So in this situation, we have 0.04 meters of travel. That means we only actually need quarter of a Newton of force. So by making us go a longer distance, we get to use less force. So this force applied times the distance traveled, this is really important. Um, we're actually going to go ahead and give this a name. Let's say this. Whenever we apply a force to an object over some distance, we are going to say that we are going to change the object's total energy. Now, we've had a definition for energy in the past. I'm going to go ahead and give it to you again. The definition for energy is uh, a substance-like quantity that is conserved and has the capacity to cause change. Most specifically, when we apply a force over a distance, this is how we're changing the energy of an object. The change in energy on an object is another name. We'll call this work. But all work is how much are we changing the energy of our object. If you're a big equation person, the actual equation that you'll probably see in most textbooks is that work is equal to the force applied on an object times the distance that force is applied. So I have a small assignment for you. If we run out of time in class, it's going to be homework, but if we have time in class, you can do this in your groups. Um, I want you to think about a ball. And if you take this ball and you apply a force to this ball for some distance, what are the different ways you can change the energy of the ball? Now, we've already talked about one. You lift it up. That must be a change in energy of the ball. But what other ones are there? Oops. Um, what other ways are there to change the energy of the ball? So that's your assignment. It's given some force over some distance. What are the different ways that we can change the energy of the ball? Going back to chem, you can kind of imagine if we were to do like an LOL diagram. Remember we had those little columns? What are the different columns? What are the different ways that we can store energy in this ball by applying a force over a distance? In fact, guess what? We'll probably end up seeing these again at some point. So tomorrow morning we'll look at a list of them, but I want you right now to think about as many different ways that we could change the energy of that ball as possible. All right, thank you very much. Have a nice day.